So here we have an exponential equation. We know that it is an exponential equation because of the exponent having a variable. We want to solve for that variable. The first thing that we have to attempt to do is get the same bases. Notice we have a base of 3 and a base of 81. Not the same. However, we can change 81 to a base of 3. That would be 3 to the 4th power. And so now we have 3 to the x plus 1 equals 3 to the 4th power. Since we have the same bases, the exponents must be equal. So our next step is to write this as x plus 1 equals 4. Now we solve for x, subtract 1 from both sides, so x equals 3. Remember, you should always check your work, and we should be able to easily see that 3 raised to the 3 plus 1 should equal 81. We're asking ourselves if it is equal in fact. This becomes 3 to the 4th power, which is 81, and that works out. Now we're going to move and look at a little more difficult equation. This equation involves the natural number e, and will require us to use our properties of exponents, We have some of the same bases, but here's where our problem lies. We have a multiplication symbol on the right side. We have a power raised to a power. And we also have e in the denominator of a fraction. So we need to rewrite this right side of the equation in order to make it work. So the left side of the equation is going to stay just like it is, equal to, here, if we remember our properties of exponents, powers to powers means that we multiply. So this simply becomes e to the 2x times, and in order to get this to work well, we want to take this out of the denominator. So when we move it up, this becomes e to the negative 3. Now, the next property of exponents we're going to use is that when we multiply powers with the same base, we simply add their exponents. So in our next step, this is going to be e to the negative x squared equals e to 2x minus 3. I did say add. When we add a negative, it's the same thing as subtracting. Now again, here we are with the same bases, so the exponents have to be equal. And now we have an equation we can solve. We should notice that this is a quadratic equation, so I will get one side equal to 0 and solve it hopefully by factoring, but if not, then I may need to use some other method. If I look, I should be able to factor this. Negative 3 has factors of positive 3 and negative 1, so this is x plus 3 times x minus 1. And we set each one of these factors equal to 0 using the zero product property. X equals negative 3 and x equals 1. Now, let's look at a more real-world problem. Between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at a rate of 12 cars per hour, or 0.2 cars per minute. The following formula from the field of probability can be used to determine the probability that a car will arrive within t minutes of 9 p.m. The function of time is equal to 1 minus e to the negative 0.2t. Now, let me try to get rid of something in here. Of course, it's not going to go away. Let me try one more thing here. I don't know what this, oops. And let's see if we can get that out of here. Alright, let's come back here. Alright, so this is our function. We notice that we're subtracting our exponential portion of the equation from 1. We also notice that the exponential portion up here is negative, which lets me know that this could be represented in other terms as a fraction. Let's go ahead and look at the problem here. Determine the probability that a car will arrive within 5 minutes of 9 p.m. Well, if we go back to the problem, this function gives us exactly that. All we have to do is evaluate the function at 5. So that's what I'm going to do now. The function evaluated at 5 is equal to 1 minus e to the negative 0.2 times 5. Now the best thing to do in this situation, especially since e is an irrational number, is to use our calculator to type this in. Let's clear that. Okay, so this is going to be 1 minus e, which is going to be second in the natural log button, and this is going to be negative okay, let's try to clear this off. Okay, we need the e, negative 0.2 times 5. Okay, and now we can hit enter, and that would be our function value. Let me bring that back up real quick. 6.632, so let's say 0.63, which is 63%. That's a 63% probability. That's pretty high. Alright, let's look at the next one. Determine the probability that a car will arrive within 30 minutes of 9 p.m. Go back to the calculator, and I don't want to retype all of that, especially with the trouble the calculator seems to be giving me. So I'm going to do second, enter, and it brings up the same function that I just typed in, and I'm going to arrow over and change that 5 to a 30. And close the parentheses, press enter, and notice that it is 0.997. And I'm not going to round it up. I'm going to write it out as 0.9975. So the answer here is 0.9975, which is 99.75% probability. That's quite close to 1. Now, the next question I have here is, what value does f approach as t goes to infinity? And when we say t goes to infinity, that's increasing without bounds. T is increasing without bounds. So as t gets larger and larger and larger, what is happening? What value is it approaching? So we could quickly try to go to a graph. 1 minus negative 0.2 x. And let's look at this graph. I'm going to set my window a little bit differently. I want my min to be negative 1. I want my max to be 5. I'm going to count by 1. My y min, I want to be negative 5, let's say. My y max, no, let's come up here, excuse me. My x max needs to be 10. My y min, negative 5, but my y max needs to be 5. Okay, and we will graph that. So, what value does f approach as t goes to infinity? Let's go ahead and look at this graph. Oh, this is kind of hard to see, isn't it? Let's go ahead and check that window again, and I'll make that y min a negative 1. So negative 1 Oh, wait, that went down too far. Clear. Resolution, we're going to bring that to 1. Alright, -1. Alright, and let's look at that graph. That looks a little bit better. But what do we notice here? That as it continues to go up, it's not crossing that 1. We can even change the window so that we can see that large x value of 30 that we just looked at. Let's look at that graph again. It's still not going past 1. So what does that tell us? Well, as t goes to infinity, as t approaches infinity, the function f of t is approaching 1. Now let's think about that for a minute. The equation, the function, was representing the probability that cars would arrive between 9 and 10, or within a certain amount of time of 9 o'clock. The probability, remember, can only be between 0 and 1 in a real world setting. So this makes sense that we can only approach 1 up to this point. Now, here's a new question. Within how many minutes of 9 p.m. will the probability of a car arriving equal 50%? Wow. Now remember, 50% is the same thing as 0.5. And in our two other answers, we got decimal values that we converted to percent. So this is really what we're looking for. And that 0.5 is a function value. F of t equals 0.5. We want to know what's the t that makes that happen. So let's go back to our calculator. And one way that we can do this is we can go to y equals, and in y equals 2, or y2, we're going to put the constant 0.5. And what that's going to allow us to do is get an intersection point. But I also noticed that, since my value is approaching 1, I'm going to go ahead and change my window before I graph and get my y max to be a 1, so that I can more clearly see what the intersection is going to be. So I'm going to make that a 1. Now I want to look at that graph. Look at that. And you'll notice that this is where the intersection is going to occur. So we want to go to second trace. Second trace to calculate. We're going to calculate the intersection number 5. And one of the great things about using the intersect feature is you really don't need to use the arrows. I'm going to use the arrow just a little bit to kind of get it a little bit closer to that point. And it really doesn't have to be on it. Notice the question is first curve. When you press enter, it's on the logarithmic equation. It's on the line for the second curve, and then you're guessing. And here we go. So this tells me that approximately 3.5 minutes within 3.5 minutes of 9 o'clock, so about 9:03 p.m., 9:04 p.m., somewhere between there, a car will arrive. The probability is 50%. That's exceptional. But think about the problem. 12 cars were arriving each hour. So, alright. So we solved some exponential equations, and in all honesty, if we think about what this equation is asking us, if we set this up in the form of a function to solve, it would be 0.5 equals 1 minus e to the negative 0.2t, and we'd be looking for t. How do we solve something like that? Well, that's our next step. So let's move on and look at solving logarithmic. Now, some of you might say, well, how are logarithmic and exponential related? Well, remember, we first talked about the fact that they are inverse functions, meaning that logarithms undo exponential equations undo logarithms. So we're going to use that concept here. Remember that the general form of a logarithm, if we use general letters. Log base b of x equals a. That means b to the a equals x in some form or another. So here, what we're going to do is actually we're going to rewrite this in an exponential form. 3 to the second power equals 4x minus 7. That is a simple equation to solve now. This 3 squared is 9 equals 4x minus 7. Add 7 to both sides. And then divide by 4. X equals, whoops, I went too fast for myself. X equals 4. And then you should check it. 4 minus 16 is 9. Log base 3 of 9 equals 2 is correct because 3 to the second power does in fact equal 9. Alright, this other side, notice that x is our base. Now we have to remember that our base cannot be negative. Alright, there are restrictions on the base. So we're going to start off the same way. We're going to rewrite it as an exponential equation, or in exponential form I should say. X to the second power equals 64. And how do I know that's not an exponential equation? Well, the exponent does not contain the variable. Notice the variable is the base of the exponent. So this is not an exponential equation, but this equation is an exponential form. It's in fact a quadratic equation. And a quadratic equation in this form, remember, mess squared is equal to mess. Well, we simply take the square root of both sides. And so we get x is equal to plus or minus 8. However, now in algebra, remember, it's plus or minus that number. Because 8 squared is 64, and so is negative 8 squared. However, the logarithm's base cannot be negative. So x simply equals 8. The negative is eliminated as an extraneous solution. Now, what about e to the 2x equals 5? In our first discussion about exponential equations, and this is in fact an exponential equation because of the x in the exponent, we said that we need to attempt to get the bases the same. Is there any way that we can get 5 to be a base of e, or e to be a base of 5? No. So we need another method to solve this. One method is to change this to a logarithmic expression. A logarithmic equation, excuse me. 2x equals the log base e of 5. Now some of you are going to say, wait. He never written log base e, and you're right. Log base e is normally written as the natural log. So this is the equation we have. Now to solve this for x, we simply divide the natural log of 5 by 2. This would be your exact answer. If you're looking for an approximate answer, you can then type that into your calculator to get that approximate answer. Okay, so now, what about this function, 2 to the x equals 5? We can do it the same way. We can write this as x equals the log base 2 of 5, which that's an exact answer. That's as simple as it can get. Or we can take the natural log or the log of both sides. 2 to the x equals 5. We can say, okay, this is the natural log of 2 to the x equals the natural log of 5, wherein we apply the properties of logarithms. The log of some base raised to an exponent is that exponent times the log of the base. And again, this is a division. X is equal to the natural log of 5 divided by the natural log of 2. Now some of you would tend to tell me that this is not equal. These two forms are not equal. They are in fact equal, because remember, I can do this as log or natural log because I'm doing both sides. I could have written log, and gotten log 5 divided by log 2 using common logs, log base 10. Here, if I use the change of base formula, because I cannot put log base 2 on my calculator, the change of base formula would allow me to write that as log 5 over log base 10 of 2. And these two functions, or these two expressions, would in fact give me the same result in the graphic calculator. Alright, here's a challenge. Now, obviously, 5 cannot be changed to a base of 3, and 3 cannot be changed to a base of 5. So we can't simply drop the bases in this case. We're going to need to do a little bit more. Based on our last slide, one of the things that we can do is raise both sides to a log, or natural log, and I tend to use natural log because it's left to right. So the natural log of 5 3x minus 2 is equal to the natural log 3 to the 3x plus 2. Now we have to apply the properties of logarithms, which tells us that we can take these exponents and bring them to the front and multiply them by the logarithmic expression. So this will be x minus 2 times the natural log of 5 is equal to 3x plus 2 times the natural log of 3. Now, some of you might think that it would be easier to divide by the natural log here, but we would still end up needing to multiply out because we have x's on both sides, and we can't bring them over since they're involved in multiplication. So we need to distribute those natural logs before we can move things to separate sides. So this is going to be x times the natural log of 5 minus 2 times the natural log of 5 equals 3x times the natural log of 3 plus 2 times the natural log of 3. Now we can get like terms together. Here I'm going to have 3x times the natural log of 3 minus x times the natural log of 5. And over here I'm going to have negative 2 times the natural log of 5 minus 2 times the natural log of 3. Notice that this left side is all constant. This is a constant number. Don't know the exact number, don't know the approximate number, so I haven't typed it in my calculator, but it is a number. Over here we still have a variable. So notice I have two x's, and I'm trying to get x completely by itself. So I'm going to factor that x out. So I have negative 2 times the natural log of 5 minus 2 times the natural log of 3. And you could factor out negative 2 here if you'd like. Really not necessary, but you could. Equals x times 3 times the natural log of 3 minus the natural log of 5. And last but not least, we want to get x by itself, which means we're going to divide by this function, this expression. So this will be negative 2 times the natural log of 5 minus 2 times the natural log of 3 divided by 3 times the natural log of 3 minus the natural log of 5 equals x. And this would be a constant number. This is the exact expression, the exact answer. Again, if you want an approximate answer, you would simply need to put that into your calculator, making sure and taking care to do your numerator in one set of parentheses and your denominator in another, so that you don't make the calculator do the wrong sort of operation. Alright, and that concludes our lesson on solving exponential and logarithmic equations. And be sure to use this information wisely, and if you have any questions, please let me know. Remember, you can always find me at mathmandy@yahoo.com. Have a good night.